Hello everyone, I'm Professor Harrison, and welcome back to our module on probability for finance. Today we're going to be covering the normal distribution and z-scores, two of the most important ideas in all of statistics. We're following Danny, a gambler with a mountain of debt, working his way through a box of mysterious letters addressed to his late father, trying to understand what happened to the family fortune. Today he's trying to figure out how returns for one equity still sitting in Victor's estate are actually distributed. He opens up another one of those mysterious letters. The normal distribution is the most important probability distribution in all of finance. That's not an overstatement. It ends up showing up in almost every quantitative model you'll encounter, from option pricing to portfolio construction to risk management. So let's start with what it actually is. A random variable x is said to follow a normal distribution if it follows a distribution that looks something like this. This distribution is often referred to as the bell curve. This bell curve distribution has a few properties that make it very useful to work with in finance. The first property is that it is symmetric around the mean. So the left side of the mean and the right side of the mean have mirror images of one another. That means the skewness of this distribution is zero. The second characteristic is that it's completely described by just two parameters, the mean mu and the variance sigma squared. The mean defines the exact center of the distribution, and the variance will describe how far from that mean you can end up landing. The third characteristic of the normal distribution is that you're more likely to land closer to the mean than you are further away from it. This is very useful in finance, where things like returns will typically be very small in a given day, but occasionally returns will end up being very large, they'll fall very far from the mean. So being able to model instances where average outcomes are more likely makes it so that we are more tractable to what's actually happening in the world of finance. The fourth characteristic is that the kurtosis of the normal distribution equals 3. We call that normal kurtosis. The tails are thin enough that extreme outcomes are rare, though not as rare as some people might assume. The fifth and final characteristic of the normal distribution, and this is one that comes up quite frequently, is that linear combinations of normal random variables are also normally distributed. For example, let's say we have two random variables x and y. Both have their own means and standard deviations, and both are independent of one another. If we were to then take a and multiply it by x and b and multiply it times y and then add them together, the resulting outcome would end up being normally distributed as well. The mean of this outcome would be a times the mean of x plus b times the mean of y. It's similarly easy to calculate the variance of this new distribution. In fact, we just have to take a squared and multiply it by the variance of x and then add b squared times the variance of y in order to get the variance of this new distribution. This is why portfolio returns end up being normal when the underlying assets are assumed to be normal. The math works out fairly easily due to these assumptions. One of the most useful facts to memorize about normal distributions is what's usually called the empirical rule, or the 68-95-99.7 rule. About 68% of observations fall within one standard deviation of the mean on a normal distribution. About 95% fall within two standard deviations, and about 99.7 fall within 3 standard deviations. Take adult male heights as an example. The mean is roughly 5 feet 10 inches with a standard deviation of about 3 inches. So under the normal model, about 68% of men end up being between 5'7" and 6'1". About 95% fall between 5'4" and 6'4", and virtually everyone, 99.7%, will fall between 5'1" and 6'7". You could check those ranges against anyone you know and they'll probably hold up. The rule is that predictable. Now apply the same logic to a stock with a daily expected return of 0.04% and a daily volatility of 1.5%. About 68% of days produce a return between negative 1.46% and positive 1.54%. About 95% of days fall between negative 2.96 and positive 3.04%. And only about 0.3% of days, roughly 1 in every 300, produce a return beyond plus or minus 4.5%. Take a moment to think about what that means. Returns beyond 3 standard deviations away from the mean are supposed to be almost non-existent. But in reality, returns beyond 4% are actually relatively commonplace. This is an example of where the normal distribution sometimes starts to break down in reality. We'll end up revisiting this shortcoming later in the course. So now let's talk about z-scores. The standard normal distribution is a special case of the normal, mean equal to 0 and variance equal to 1. The cumulative distribution function of the standard normal is denoted capital Phi of z, which gives you the probability that a standard normal variable falls below z. The reason the standard normal is so useful is that it lets you convert any normal random variable into a standardized form. The z-score of x is defined as x minus mu divided by sigma. What you're doing here is measuring how many standard deviations your outcome x will sit above or below the mean. We subtract the mean to center things, and we divide by the standard deviation to remove the effects of variance. And this effectively leaves us with a standard normal distribution. This makes things much easier to calculate probabilities, things like the cumulative distribution function, when we're dealing with normal distributions. Here's a worked example. Take 2 of Victor's holdings. Stock A had an annual return of 15%, and historically it had a mean of 10% and a volatility of 20%. Stock B returned 8% this last year against its mean of 5% historically with a historical volatility of 10%. Stock A's z-score is going to be 0.15 minus 0.1 divided by 0.2. That gives 0.25, or 0.25 standard deviations above the mean. Stock B's z-score is 0.08 minus 0.05 divided by 0.1, so that gives 0.3. Now look at those two numbers. Stock A produced the higher raw return, but on a risk-adjusted basis relative to its own mean and volatility, Stock B actually is the one that outperformed. Stock B was 0.3 standard deviations above its expected value, while Stock A was only 0.25 standard deviations above. The z-score is what makes this comparison possible. Without it, you're comparing apples to oranges. The z-score strips away the units and scales the differences. What you're left with is a pure measure of how unusual a given outcome actually was. Danny puts down the letter. Victor's estate still holds one active equity position. He has a year of daily closing prices on it, about 250 data points. He's been staring at big loss days, wondering which ones he should actually worry about. So he runs the numbers. He estimates the mean daily return and the daily volatility. Then he calculates a z-score for each notable bad day. Most of them end up being between -1 and -2. A couple hit -2.3, one bad week produced a day at -2.8. Under the normal model, none of those are really outliers. They're all within the range of what you'd expect to see across 250 trading days. He then does the same thing with his own gambling history. He's been keeping a record, session outcomes, stakes, results over the past few years. He pulls up a stretch where he's been gambling with one of his magician friends, and he's been losing quite severely. He calculates the average loss over the course of his time playing with this new magician friend and finds out that it's almost 5 standard deviations below the mean of what he normally does. He realizes how unlikely this outcome could possibly be because of the fact that his magician friend also has some serious skill when it comes to sleight of hand. With this realization, he decides that he's either not going to gamble with his magician friend, or he's going to be the one that deals the cards next time. Without this normal distribution framework, he would not have been able to calculate how abnormal these losses truly were. So that's the normal distribution and z-scores. The normal gives you a complete model of random variables using just 2 numbers, the mean and variance. The 68, 95, 99.7 rule lets you translate those numbers into probability ranges quickly. And z-scores let you standardize any normal variable onto a common scale, so you can compare outcomes across completely different assets or situations. The z-score is what lets you move from how big was this result to how unusual was this result, and those are very different questions. Both of those end up being foundational for everything we do in inference, risk and management, and portfolio construction going forward.